All right, so finishing up with 14.3, we wanted to talk about this idea of the differential. So what the differential does is basically tell us how much my function might change if I change both x and y at the same time. It doesn't give me the actual function value, it just tells me how it might change. So let's go back and look at the tangent plane idea again. So we have a surface, so this is my surface, and then we have some point AB, and we said we could find the tangent plane to AB, and that at AB, and that what the tangent plane did, the surface would do near there in a similar way. So if the tangent plane increased, the surface would increase. So thinking about that, I can kind of think about, what if I want to move not just in the x or y direction, but I want to move like that. I want to move in both directions, and I want to know what's happening on my surface. Did my surface increase? Did my surface decrease? And by how much? Just the partial derivatives alone only tell me what happens if I move in one direction by itself. If the partial derivative with respect to x is positive, I know that my surface will increase when I move in the x direction, but maybe the partial derivative with respect to y is negative, which means if I move in the y direction, my surface is going to decrease. So the question might be, what if I moved a little bit in both? What would be the final outcome? So that's what the differential tells us. If we think back to what we just discovered about the tangent plane equation told us that my function, which is a function of f of x, y is the surface, can be approximated in value by the equation of the plane. And we said the equation of the plane would be the z value, which would be the same on the plane as for the function. So if I'm at the point AB, the z value would be AB. This is my point right here on the surface. That would have coordinates AB, f of AB. And I'd plug it into that function and get whatever that z value is. It's going to be on my surface and on the plane. And then using our equation of a plane from chapter 12, I would take the slope in the x direction, which would have to be the rate of change with respect to x. So the partial derivative with respect to x times x minus a. Then I would add the slope in the y direction, which is the partial derivative with respect to y, times y minus b. If we rearrange this for a little bit, I'm going to subtract from both sides the f of AB. So now we have f of xy minus f of AB is approximately equal to, I'm going to come over here to give myself some room, the partial derivative with respect to x times x minus a, plus the partial derivative with respect to y times y minus b. Let me make my y look a little bit more like a y. So now we've just kind of rearranged the tangent plane formula, so it tells us a little bit something different. We can use it in a different way. This right here, f of AB is a specific z value. That's that point that's tangent. This represents a change in output, right? That's my change in d. So I'm going to call that d for difference or change in f, the change in my function. Similarly, if I look at x minus a is a change in x. That's the difference between x and some point a. So that could be thought of as a delta x or a dx, a small change in x. And following that same idea, y minus b is a change in between y's. That's moving from a point on my surface with the y coordinate y to my original point b. That's a change in y. I can call that dy. So if we sort of rewrite this, then what we have is the change in my function value would be the partial derivative with respect to x at AB times dx, the change in the x direction, added to the partial derivative with respect to y times dy, the change in the y direction. And that's the formula we started with that they call the differential. Another way to look at this that I think is helpful, remember df is just your change in z. If I think about what the partial derivative with respect to x, what that means, that's basically my change in z as I change x. And dx is basically my change in x. The partial derivative with respect to y, that's my change in z as I only change y, and I'm multiplying that by a change in y. So those cancel out. So what I can see this tells me is I'm adding both the changes in z's together. I'm finding out how much does z change when I moved in the x direction, how much is the z changing for that amount of movement in the y direction, adding them together to get the total change in the function. It does not tell me the function value, it just tells me how much it changes. How and when might I want to use that? One example might be, we'll talk about one example conceptually, and then we'll do one with actual numbers from the homework. So one possibility might be the function that we looked at earlier. You have your balance, depends on your principal, e to the RT, where remember in this case, both the principal and time are both going to be variables. So I could say that the change in my balance is going to be equal to the partial derivative with respect to P, the principal, at some given point AB, and times my change in P, so we'll say dP, plus the partial derivative with respect to T at some given point AB, times dt. So what would this tell me? This isn't going to tell me the actual balance, but maybe there's a scenario where I have a different amount of money. Maybe it's sort of a risky investment, but it has a high interest rate, and I'm thinking I could invest $500 or I could invest $800, and maybe I could leave it in there for 5 years or 10 years. So this would let you say, okay, if the change in my investment is, I added an extra $300 and I add an extra 5 years, how much extra money am I going to make? It doesn't tell you what your total balance is, but you can say, yeah, for adding an extra $300 and an extra 5 years, I'm going to add an extra $1,000 to my balance. And you might think, oh, that's worth it. I'm going to wait the 5 years. Or maybe you figure out I add an extra $300 and an extra 5 years, and I'm only going to make an extra $100. You're like, ooh, well, that's not worth my waiting so long. But maybe if I increase this change in my principal, I add even more, maybe that will give me more. So that would be an example of why you might want to use this or consider just the differential. Another way to apply it using the actual formula would be like in one of our homework problems. So in this case, they've given us a point P, they've given us a point Q. These are inputs, right? We're talking about a function of two variables. So I've got two inputs, one output, and they gave me the output at P. And then they're telling me, they're not giving me the function, but they're telling me the partial derivatives, and they want me to estimate what's going on with this function at Q. So I'm going to draw this as if we have a contour diagram. So what they're saying is over here at the point 5,8, this is point P. I don't know exactly what the function looks like, but I know the function value at P is 8. So I don't know exactly what the contour shape is, but I'll just draw something like this. That value at 5,8 is 8. Now what I'm going to do is I'm going to move a little bit away from that point, right? The derivatives are still going to help me because notice I'm staying very, very close to that point. So I'm going to assume the rate of change is going to be pretty close to the derivatives there because I'm in a very close proximity, a very close neighborhood. So now I'm going to 4.97. So I'm going to move from here. I'm going to move, 0.03 units to the left. And then from this 8, I'm going to move down 0.01. So I'm moving down and over, and this is my point Q. And the question is, what would now be the new value at Q? I know that I moved in the x direction, so we'll say dx, my change in x, is negative 0.03 because I went from 5 to 4.97. And I know that my dy, the change in my y direction, is negative 0.01 because I went from 8 to 7.99. And the first question I'm going to ask myself then is how much did my function value change by? So that's where I can use the differential because they did give me the derivatives. So the change in my function is going to be my partial derivative with respect to x. They're calling this function g now. Sorry, I should call this dg. The partial derivative with respect to x times my change in x plus the partial derivative with respect to y times the amount I changed in the y direction. And that gives me, in this case, negative, put this in the right order, negative 0.2, which is given to me as the derivative with respect to x times negative 0.03, what we computed as the change in the x direction, plus negative 0.3, which is given to me as the partial with respect to y, times negative 0.01, which we computed as the amount of change we're going in the y direction. And if we multiply and add that correctly, we should get that the change is positive 0.009. So that tells me how much my function changed by. Since I happen to know where my function started here, it told us that we started at 8. I can now say that g of q is going to have to be g of p where I started plus 0.009, because I now know the differential, the amount my function changed by, was went up by 0.009. So adding together in this problem, we started here with 8, that was given, and we added 0.009. So if I have a function with those derivatives, I would expect the new value now to be 8.009. All right.